Afternoon. I'm Spot On Weather meteorologist Matthew Euler. Welcome to my latest training video. And in this video today, we're going to examine semi-permanent pressure systems and jet streams. Starting off with an overview of today's training video. Again, we'll talk about semi-permanent pressure systems, and then we'll talk about the jet streams overall. The semi-permanent pressure systems talk will be rather brief, but we're really going to focus a majority of today's training video on jet streams. All right, so let's first talk about semi-permanent pressure systems. Let's do a quick overview of this. Basically, we have differential heating that occurs across the Earth, across the latitude belts. This differential heating between the equator and the polar areas really sets things in motion. It begins the process of the general circulation. Now, the general circulation is going to produce 7 semi-permanent pressure systems. All right, so 7 semi-permanent pressure systems. And these systems will migrate with the sun's changing positions throughout the seasons. So let's take a look and examine upper left here. And I believe this is, let's see, yeah. So this is January over here. This is the January semi-permanent pressure location, so to speak, and how things are set up in January in the northern hemisphere and in the southern hemisphere as well. Here's the global semi-permanent pressure systems for the month of July over here on the right. So starting with the upper left, let's take a look at a few things that really stand out on this particular diagram. The first thing I want you to note are these semi-permanent low pressure systems. We have one here in the northeastern Pacific. We also have another one over near Iceland. So the one near in the northeast Pacific here is called the Aleutian Low semi-permanent pressure system. The one over here on the right of the left-hand graphic here, that is known as Icelandic Low. And you'll notice these pressure systems, they generally are going to semi-permanently exist in these locations, the northeast Pacific and the North Atlantic. And then in between on the continents, let's examine the continents. So Siberia, we have high pressure in January. We also have high pressure over the North American continent. And then we have high pressure also over here on the far right. That's part of that high pressure cell over Siberia. So bottom line is when we look at the Northern Hemisphere specifically in the month, this is going to be January, okay, over here on the left. When we look at the month of January, we notice that the lower pressure systems are more expansive and they tend to exist over water, okay? And the high pressure exists over land in January because of how cold the continental areas are as compared to the nearby water. Over on the right side here, you'll notice how things have changed over here in the Northeast Pacific. Notice how we now have this H, this letter H in place of where the L used to be on the left in the Northeast Pacific. This is the Eastern Pacific high pressure system, and it generally is going to expand poleward or to the north in July. Similarly, over here on the right, across the Atlantic Ocean in the month, again, this is going to be July. I'll abbreviate this JUL. In July, we have the Bermuda High, or the Azores High, which is going to be much more dominant, expanding poleward in the month of July. Notice how the low pressure systems are much weaker and they're generally more confined. You don't really see the reflection over here over the Aleutian Low situation here on the right, but trust me, the high pressure systems of tropical highs are going to expand in the summer poleward and they're going to retract. Look over here on the left now. Let me see if I can find my cursor again. There we go. All right, so over here on the left, again, look at that graphic. Look how suppressed this high pressure system is. The East Pac High in the wintertime closer to the equator. And the same thing here across the Atlantic. The Bermuda Azores High is much further south. Now, when we talk about the southern hemisphere and semi-permanent pressure systems, we really do need to mention that, the southern hemisphere has more water than the northern hemisphere, less land masses in the southern hemisphere. So in general, when we talk about January in the southern hemisphere, we're talking about their wintertime. Their summertime. Excuse me. In January, it's our wintertime in the northern hemisphere, and the southern hemisphere is summertime in January. So you see how these H's are much more expansive in both the Pacific side off the coast of South America, and then also over here in that'd be the Indian Ocean area, right down. No, actually, that's the South Atlantic there. Sorry. So South Atlantic, it's expansive. The Indian Ocean, Southern Indian Ocean, the high pressure is more expansive in January. There, summertime. In July, these high pressure systems still are influential in the southern hemisphere. They're just not as expansive as they are in January. All right, so now let's jump into a talk about jet streams. This is really what this training video is all about. Jet streams consist of strong horizontal winds concentrated in narrow bands. We have two main jet streams that we'll talk about. We have the polar front jet stream and the subtropical jet stream. Let's take a look. With the polar front jet stream, its main cause for its existence is a strong horizontal temperature contrast. We have really some intense heating over the tropics. This results in higher heights and thicknesses because we talked about this before in my previous training videos. The warmer the air is, the greater it's going to expand. That's going to result in higher heights and higher thicknesses. Cooler air at the poles, meanwhile, causes the air to contract. This results in shallower thicknesses and lower heights aloft. Just in my most recent video, I talked about how colder air is going to result in lower heights aloft. Now, the contrast in heating and cooling creates a north to south temperature gradient across the latitudes. But specifically, we have a very sharp, for the polar front jet, we have a very sharp type of temperature gradient, north to south temperature gradient, near 60 degrees north and south latitude. And this area is generally known as where the polar front will hang out. So temperature change is going to be greatest near that polar front, around 60 degrees north and south latitude. You're going to get a strong temperature gradient or a strong temperature difference, which is going to be equivalent to a strong thickness gradient. Just think about this. Temperature and thickness are directly proportional to each other. So if I increase my temperature, I increase my thickness. If I decrease my temperature, I decrease my thickness. So colder temps, lower thicknesses. Higher temps, higher thicknesses. So there is a directly proportional relationship between the temperature and thickness of the atmosphere. Now, this change in thickness with the stronger temperature gradient gives us a change in heights. A change in height per unit distance is going to be known as the contour gradient. So just like we talk about on the surface of the Earth, we have what's known as the pressure gradient. We also have a gradient aloft with our heights, and this is known as a contour gradient. All right, so with the polar front jet stream, just like we have a pressure gradient force, we have a change in heights over a specific distance, okay, up above the surface. And this is known as a contour gradient force. This initiates the wind in the upper levels of the atmosphere. We have a stronger contour gradient force is going to yield greater wind speeds. It's going to result in the formation of a jet stream. Now, Coriolis force is going to turn these strong winds toward the east, resulting in the west to east jet stream. All right, and this is going to occur in the mid-latitude westerlies. We get a west to east jet stream. So we have a contour gradient force. This initiates the wind, okay? This is going to get the wind speeds really kicking up and form a jet stream. Then we get the Coriolis force, which turns these winds to the east, resulting in the west to east jet stream. And the stronger the temperature gradient, the stronger the polar front jet's wind speeds are going to be. And this is primarily going to occur in the winter season when we have a much larger latitudinal temperature change over shorter latitudes or distances. The polar front jet, by the way, also because of wintertime, it's going to reach its lowest altitude in winter because colder air is going to be more shallow and it's going to go further south from the polar areas during the winter season. All right, so let's examine what we have here. You know, the polar front jet is abbreviated with the initials PFJ. You see the graphic here on the left. And so generally, okay, let's just review real quick. From the surface to this solid dash, or the solid black line here, from the surface to this solid black line is the tropopause. This is where most of our weather is going to occur, in the troposphere, okay? So notice what happens at about 60 degrees north latitude within the troposphere. You see this polar front jet, or the polar front itself rather, sets up where you have colder air invading warmer air. The warmer air is going to be lifted aloft in the vertical, right here. And that's going to cause the height of the tropopause to be higher in the warm air. But behind the polar front, we have colder air, and you notice how the temperatures drop. The overall upper level temperatures here, the negative 35 degrees Celsius isotherm, gets lower in altitude in the colder air, as does the height of the tropopause. And then in between, there's like a break in here between the height of the tropopause, it's lower in the colder air, and the height of the tropopause out ahead of the polar front in the warmer air. And so you have a break in the tropopause here at about 60 degrees north latitude, at an altitude between 10 and 15 kilometers above the Earth's surface. And this is where your polar front jet is going to form. It's going to form in that break or that fold of the tropopause. A couple other tidbits here about the polar front jet here on the right on this table, showing it's strongest in the wintertime. It's also lowest in altitude in the wintertime with the colder temperatures, and it goes further equatorward in the wintertime, further south. In the summertime, the polar front jet is weaker, it's higher in altitude, and it's also more polar or further north in the northern hemisphere. All right, so now since we've talked about the polar front jet, now let's move into the subtropical jet. Now the main cause of the subtropical jet is upper level convergence between the Hadley and the Ferrel cells of the general circulation. This upper level convergence creates a temperature gradient aloft, which leads to stronger winds. And one of the major things that results in the subtropical jet stream formation is the conservation of angular momentum. It's a major contributor to the subtropical jet stream. It's actually responsible for speeding it up. All right, so as we're going to talk a little bit more with graphics about some of these concepts, because they can get a little bit more complex and more difficult to understand. First, I want to show you this. On the right-hand side is called Newton's cradle. And in this example, we have, these balls numbered 1 through 5, and then we have this string attached to each of these balls, okay? All right, so what happens, we have a case of linear momentum when I have this graphic here on the bottom right. This first ball is going to strike the second ball, and that second ball is then going to swing out and then go back and hit the third ball. The third ball is going to swing back and hit the fourth ball. The fourth ball is going to swing back and hit the fifth ball. So basically, there's a transfer of linear momentum. There's going to be a transfer of linear momentum between all of these balls. So again, imagine this. Here comes ball 1, it hits ball 2. Ball 2 is then going to come back after the impact, and then it's going to swing back forward and hit ball 3. And then the same thing's going to happen. Ball 3 is going to go back, then it's going to go forward, and it's going to hit ball 4, and so on. All right, so the first ball is going to pass momentum to each of the balls, okay, over time. The first ball, let's say you pull the string back on this ball, you let it swing, and then that linear momentum is going to transfer to the second ball, third, fourth, and fifth ball, right on down the line. All right, with the subtropical jet stream, when we talk about angular momentum now, momentum is simply the mass of an object times its velocity. And for angular momentum, I want you to think of this ice skater over here on the right. Think of a spinning ice skater with outstretched arms. When they bring their arms out like this, see the graphic here on the right, this ice skater on the right? I want you to think about right here. This ice skater right here, okay? Notice how this ice skater spreads her arms out further from her body. That is going to increase your turning radius, okay? And this skater will spin at a slower rate. The skater on the right is going to have a slower velocity because her arms are stretched out. We're increasing the turning radius, so she will spin slower. Now that same ice skater with the arms tucked in tightly towards her body is going to decrease the radius. So let's say right here on the left, the ice skater on the left, notice how she's tucking her arms in towards her body, and she's going to spin much quicker because we're decreasing that turning radius. So increased velocity is going to result. So bottom line, this is going to show us that relationship between radius and velocity, and it's inverse in nature. So What does that mean? All right, so we said that, let's just put this out here. We say that momentum, I'll just abbreviate with a lower m letter here, equals mass. I'll make mass a large M just to make it more simple because we have two m's in this equation. Mass times velocity, okay? So if I decrease my radius, okay, so let's say I have r as my radius. If I decrease my radius, like we're doing over here with the ice skater here in the left, with the arms tucked in, I'm decreasing my spinning radius, my velocity is going to increase. Okay, so that's the inverse relationship between radius and velocity. If I increase my radius, let's do up arrow next to r for the radius, then my velocity is going to decrease. And that's what we're really demonstrating over here on the right with these ice skater pictures. All right, so if we apply this ice skater concept of radius and velocity together, let's apply this now to the concept of our atmosphere and the subtropical jet stream. So when the air above the Hadley cell flows poleward, we decrease the radius of Earth's rotation, causing the air to accelerate or increasing velocity. Anytime we go northward in the northern hemisphere, right, we're going to decrease our radius. So we're going toward the north in the northern hemisphere. Our radius of the Earth is going to be less and less as you go poleward, and that's going to result in increasing velocity of an object above the Earth's surface. Coriolis force will turn the faster moving air, giving us west to east subtropical jet stream winds. So if my winds initially were from south to north, let's say this arrow here represents, let's see, this N is north, and this is south at the bottom. And let's say I have a parcel of air, and it's going from south to north, okay? My Coriolis force is going to turn that motion to the right if it's a tended path in the northern hemisphere, or toward the east. And that's going to result in a west to east jet stream. In this case, we're talking subtropical jet. On the other hand, when the air above the Hadley cell flows equatorward, we increase the radius of Earth's rotation, causing the air to slow down. Okay? So just keep this in mind. I might have a diagram here. Yes, I do. Okay, cool. I'm going to show you this diagram here in a moment. This will really help you understand some things. Let's take a look at it. Okay, so we have the radius of the Earth demonstrated on the left. You have the North Pole at the top of the diagram on the left, okay? And then you have the equator at 0 degrees latitude over here on the very bottom line here, okay? This is your equator, 0 degrees latitude. So as a parcel of air goes northward in the northern hemisphere, do you notice how this radius, lowercase r, is getting less and less, okay? The radius is going to be the greatest at the equator because that's basically the widest part of the Earth. But as you go north, your radius is going to decrease as you go poleward. Look at the distance of this line for the radius at 60 degrees north compared to this line at 30 degrees north. See how this line at 30 degrees north is longer? All right, so bottom line here is Earth's radius is going to vary by the latitude. And as you go poleward, you decrease your radius, which is going to increase the velocity of any accelerated. You're going to accelerate your air parcels above the Earth's surface. So with subtropical jet here on the right, notice at point A, my air parcel is traveling at about 50 knots. But as this parcel of air moves northward in the northern hemisphere, we're decreasing the radius of the Earth, radius of curvature, and now my air parcel is zipping along at 100 knots. So as we move towards the poles in the northern hemisphere, we're decreasing radius, increasing velocity of the parcel, and as we go back equatorward or south, we once again decrease our air parcel velocity down to 50 knots at point C. So the subtropical jet stream and air parcel velocity, there's an inverse relationship again between radius of rotation and the velocity of the parcel of air. So when you're talking about subtropical jet, you kind of see it make this configuration. Sometimes you'll see it go southwest to northeast. Generally, your wind speeds are going to speed up as you go poleward. Right, so now let's examine, we talked about the polar front jet, which is around 60 degrees north and south latitude. We talked about the subtropical jet, which usually resides about 30 degrees latitude, 25 to 30, somewhere in there. We talked about the relationship of velocity and radius. Now let's talk about the jet stream characteristics themselves. First of all, the jet stream is thousands of kilometers long. It stretches from 2,000 to 3,000 kilometers in length. Let's see if I can get this to work now. Oh, there we go. So first things first, that's the first bullet. Second bit of information with jet streams, they're hundreds of kilometers wide, 200 to 300 kilometers, and they're few kilometers thick. They're only 5 kilometers thick. So an example of jet streams is shown on this particular diagram. The blue line represents your polar front jet, and it's usually much further poleward. And then this purple solid line represents your subtropical jet stream, which is further south. And then these two jet streams really do make a difference in the winter season. North of the polar front jet stream, this blue line, you typically have your coldest air. And then south of it, you have your warmest air. With the subtropical jet stream, really what that is it's a moisture conveyor belt. It really transports a lot of moisture from the deep tropics northward. All right, here is a diagram on the right showing you graphically what I just went over with these bullets up top. 5 kilometers in depth. Here is your width of your jet stream. It's about 200 to 300 kilometers wide. And here's your length, 2,000 to 3,000 kilometers long. All right, so we have different parts of the jet stream now we need to talk about. We need to talk about the jet core, which is a relatively uniform tube of winds within the jet stream interior, and it's continuous along the length of the jet. We have the jet axis, which is the shaft of the strongest winds through the center of the jet core. And then we have these jet maxima, these jet streaks. They're intermittent regions of stronger wind speeds along the jet axis. Just think of jet maximum or jet streaks as elliptical or football shaped, and they're outlined by these isotachs. ISO meaning equal, ISO, tachs, TACH meaning equal wind speed tachs. So lines of equal wind speed is what we analyze at a 300 millibar chart for jet stream, or the 250 or the 200 millibar chart. Again, here's the jet stream characteristics again. This is your core. All right, this is your jet axis, which has some faster wind speeds within it, and then the jet maximum is this elliptical shape. This is a top-down view looking down on the jet max or the jet streak, and this is your jet axis, this solid dark line in this example, a top-down view. All right, so jet stream maxima or jet streaks in general. These are very, 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 very important as far as atmospheric dynamics and support of our storm systems at the surface, or high pressure systems at the surface even. The highest winds are contained within the jet streak. You get divergence usually occurring within what's known as the left exit, the left front, the right entrance or rear region. And then if you are beneath the left front or right rear quadrants of the jet maxima, you are going to have upward vertical motion, and that's going to promote storm development. Upper level convergence is usually going to occur within the right exit or the right front and the left entrance or the rear entrance regions, and that's going to promote fair weather and downward vertical motion, DVM, downward vertical motion, sinking air. Let's examine these jet maximum or jet streaks, okay? First, let's look at it in cyclonically curved flow. So you notice this solid dark line here. This represents your jet axis here, okay? And you have this purple coloring here, very elliptical in shape, right? That would be your jet maximum or your jet streak in the purple shading. Okay, so in general, what we're looking at here is if this was your long wave trough axis, the solid vertical thin black line is your long wave trough axis. You're going to get upward vertical motion in this quadrant. Okay, let me just I'll draw this out for you to make this really simple. Okay, so this is cyclonically curved flow, right? So let's just divide this purple. Let's divide this purple increased wind speed here, this purple coloring indicating increased wind speed. Let's divide it into 4 pieces. Okay, so generally, let's do this. Okay, if I were to divide it into 4 pieces like this, any jet maximum or jet streak, in a cyclonically curved flow now, not in straight line flow, but cyclonically curved flow, my upper motion is going to be in this left exit region, or what's known as the left front quadrant. And I'm going to have upward vertical motion here in this green hashed area. Meanwhile, behind the long wave trough axis here, I'm going to have downward vertical motion in the left entrance region of this jet maxima or jet streak. Additionally, we can look at a straight line flow demonstration here on the left. So, by the way, this X represents vorticity maximum value. When you have an X like this, this is a 500 millibar. If I were to do a 500 millibar vorticity chart, I would analyze the vorticity. N represents your minimum or negative vorticity value. All right. So we have our active jet streak here. See this? These are your isotachs. So the deep purple in the middle here, that represents 110 knots. The lighter purple shading, 90 knots. And then the final very light purple shading is 70 knots. Okay. So we have our wind. It's accelerating from west to east in this case. Just follow this black dark line here. That's your flow. And then within this jet streak, we can divide this up into 4 pieces. Okay. Let's just divide it up. I'll put a plus symbol over it. So the left exit region over here, or I call it left front quadrant of the jet max, that's going to have upper level divergence and lifting air motion, vertical air motion. The right exit region here on the right, or the right front region, is going to have upper level convergence and downward motion, so sinking air. The right rear quadrant is also going to have, or right entrance region is going to have upper level divergence and upward motion. And then the left entrance portion of the jet maximum, this jet streak, is going to have upper level convergence and downward motion. If we were to look at it on a 300 millibar chart there on the right, let's go over here. 300 millibar chart, we're going to identify jet maximum jet streaks. This is an example of one right here. You also have another one right here with this orangish coloring here coming into Oregon from the Northeast Pacific. So you're just looking for accelerated regions of fast-moving wind speeds that kind of stand out within the jet core itself, within the jet axis. And then you would divide up the jet maximum or jet streak into 4 quadrants, okay? Okay, let's do this again here. So if this is a quad, this is one right here, we'd have upper vertical motion if you're beneath the left front or the right rear quadrants of this jet max. Let me see if I can do one here. All right, so let's say this is the jet maximum here. Okay, so this is my jet max here. I'll abbreviate it JM, jet max. And then let's divide this up into 4 quadrants. We'll just put a plus symbol over it. The left front and the right rear quadrants of this jet maximum or jet streak is going to have upward vertical motion and rising air. Right here, left front and right rear. If you are located beneath the right front or the left rear quadrants, you're going to have sinking air motion. So it's important to look to see where you're located in relation to these jet maximum or jet streaks to see if it would favor upward vertical motion, rising air, or downward vertical motion and sinking air. Upward vertical motion being associated with clouds and storminess, precipitation, downward vertical motion being associated with fair weather. So now that we identified the jet maximum jet streak, it's a specific feature within the jet core and the jet axis, let's now talk about tropopause leaves. The tropopause is discontinuous in 2 main areas that you're going to look for. It's going to be discontinuous near the subtropical ridge, which is about at 30 degrees latitude, and near the polar front at 60 degrees latitude. Now the jet streaks the jet streams break the tropopause into 3 particular tropopause leaves, and it is between these leaves that we find the jet streams. And the tropopause leaves are going to change in height with latitude. Let's first look at the tropical leaf. Now this is located equatorward of 30 degrees north and 30 degrees south latitude, tropical in the tropics. It is the highest leaf and therefore the coldest leaf because it's highest in altitude. The higher you go up in the atmosphere, the colder the temperatures get. Warmest air is near the equator, where the average surface temperature is 30 degrees Celsius, resulting in the greatest thickness there. The average height of the tropopause is up to 17 kilometers in the tropics, and the average tropical leaf temperature is negative 80.5 degrees Celsius. Notice how cold that value is, right? Because you have a warmer atmosphere, higher thicknesses, higher heights, and the higher altitude of your tropical leaf. than anywhere else on Earth, okay? So the higher you get, the colder the temperatures get. What about the mid-latitude leaf? This is our second leaf we'll talk about. So we have a tropical tropopause leaf, we have a mid-latitude tropopause leaf. Now the mid-latitude is going to lie between 30 and 60 degrees latitude. And it is lower in altitude than the tropical leaf. Makes sense because we're gaining latitude, which means it's getting cooler. It's going to be higher than the polar leaf though. And then the polar leaf is the last one we'll talk about. This is the third and final tropopause leaf. The northernmost leaf is located poleward of 60 degrees latitude. That's the polar leaf. This is the lowest leaf because of how cold the atmosphere is. The tropopause leaf height for the polar leaf is going to be lowest, but it's also going to be warmest because you're closer to the surface. The coldest air is at the poles with an average surface temperature of 0 degrees Celsius, resulting in the lowest or most shallow thicknesses there. The average height of the tropopause in the poles is about 9 kilometers, by the way. That's a big difference, right? What do we say the tropical leaf average height was? Let's go back. Average height of the tropopause, really the tropical leaf, is about 17 kilometers in the tropics, and it's down to 9 kilometers at 60 degrees latitude. And the average temperature of the polar leaf is minus 58.5 degrees Celsius. What was it, the tropical leaf? Minus 80.5. So see that difference? If we were to look at all the tropopause leaves together, now we examine these leaves again to determine where the position of the polar front jet stream and the subtropical jet stream are going to be located. So if you look at the bottom here, this line, this represents your latitudes. So over here on the far right, we're at the equator. And the average temperature at the equator at the surface is 30 degrees Celsius. That's about 86 degrees Fahrenheit. As we go northward, okay, we're going north towards the North Pole in this direction, toward the left. We're going to go to 30 north, we're going to go to 60 north, and then eventually we're going to get to an average temperature of 0 degrees Celsius, 32 degrees Fahrenheit at the North Pole. So it's a 30 degrees Celsius difference between the equator and the North Pole due to this differential heating, with the sun being most intense towards and closest to the equator with the tropics. So it's important to look at, okay? So very warm temperatures at the equator, it's going to result in warmer air, it's less dense and wants to rise. You also have greater thickness values. So look where your tropical leaf resides. Look how high it is in elevation above the equator. All right, it's also the coldest because it's highest in altitude. The subtropical jet is going to form basically between this tropical leaf and this mid-latitude leaf. So you see how there's a break in the tropopause here? This break is caused by the difference in elevation between the tropical leaf and the mid-latitude leaf. And so at 30 degrees north, look at what we got here. We have a subtropical jet stream. That's typically where it resides, in between the tropical leaf and the mid-latitude leaf in that tropopause fold or that break. And then we go further north to 60 degrees latitude, and we have the PFJ, the polar front jet stream. Generally resides around 60 degrees latitude, closest to the polar front. And notice the break between the mid-latitude leaf and the polar leaf now. That's going to be the placement or location of your polar front jet stream. So the colder temperatures are over here on the left with the North Pole. Colder air is going to be denser. There's going to be lower thicknesses and a lower elevation to the polar tropopause leaf as compared to the mid-latitude leaf and the tropical leaf. But these breaks are so very important. Just remember, subtropical jet is located between a break in the tropical leaf and the mid-latitude leaf. Polar front jet is located in a break between the mid-latitude leaf and the polar leaf. All right, so hopefully you understood that. Some of these concepts are a little trickier to understand, but hopefully I broke it down well enough for you to really get something out of the training today. Let me go back. Yep. So in review, we looked at semi-permanent pressure systems. January was on the left. This was January on the left. In the northern hemisphere during wintertime in January, we have lower pressure. The Aleutian low and the Icelandic low are stronger, and they generally reside over water. Aleutian low in the vicinity of Aleutian Islands towards the Northeast Pacific, and then the Icelandic low in the vicinity of Iceland. And then we have continental cold high pressure cells that set up over the colder continental land masses of Siberia and North America during the January timeframe. Over here on the right in the northern hemisphere, the high pressure subtropical highs expand northward with the sun. They're also much stronger in the summertime, specifically in July. So we're showing you an expansive look of high pressure now over the water areas, and the semi-permanent low pressure systems near Iceland and Aleutian Islands really dramatically weaken. We then went into jet streams, which are just strong horizontal winds that are concentrated in narrow bands in the upper portions of the atmosphere. We looked at two specific jet streams, the polar front jet and the subtropical jet. With the polar front jet, the main cause is the sharp temperature contrast across across certain areas, specifically greatest heatings over the tropics, coolest airs at the poles. So you get a front that forms at 60 degrees north and south latitude. This is known as a polar front. That's where your greatest heating and cooling contrast is located in the northern and southern hemispheres. We talked about where the temperature change is the greatest. Temperature and thickness are directly proportional or related to each other. If you increase temperature, you increase thickness. If you decrease temperature, you decrease thickness. We talked about a contour gradient force, which initiates the winds in the upper levels that results in this jet stream forming. And the Coriolis force is turning things to the right of intended path of motion towards the east. So we get a west to east jet stream in the middle latitudes between 30 and 60 degrees. And the stronger the temperature gradient, specifically in the winter, the stronger the polar front jet. So summertime, that polar front jet's going to be much weaker. In wintertime, those wind speeds within the polar front jet are going to increase drastically. And then we talked about, where's the polar front jet located? Generally, again, around 60 degrees north latitude. If we went straight up, we'd see that. These tropopause levels do decrease as you go towards the polar areas due to the colder temperatures. Some other example or facts here: winter versus summer, polar front jet, strongest in the winter, weakest in summer, lowest in altitude in the winter, and highest in the summer, and then further equatorward or southward in winter as compared to more poleward in winter or summertime, more poleward in summer. The subtropical jet, we talked a little bit about that, with the conservation of angular momentum being a big contributor to it. And we talked about the spinning arms, the ice skater. And we talked about the fact that radius and velocity are inversely proportional. So if we decrease radius, we increase velocity. So if with the subtropical jet example, the further north you go, here we go, the further north you go, the less the radius, the lower the radius as you go northward in the northern hemisphere. And that's going to result in an acceleration of the velocity of the air parcel. So you typically see the subtropical jet stream, it will speed up as it goes poleward. It will slow down as it goes southward or equatorward. Here's the radius depictions again here of Earth on the left. And then we talked about jet stream characteristics, jet core, jet axis, the jet maximum. Jet streaks very important for everyday weather as far as surface low pressure and surface high pressure development and strengthening. Generally, where in relation in the jet maxima or jet streak do we find upward rising vertical motion of air, where the clouds and the precip are going to be, and downward vertical motion of air where you're going to have nicer weather with high pressure. We went ahead and drew it out a little bit here on the left, and then I showed you an example. If we were looking at a 300 millibar chart, and by the way, this graphic here, this legend on the right of this 300 millibar chart on the right, that represents your wind speeds. Okay, so the oranger colors are stronger, again approaching the Pacific Northwest in this example. We also have one here, a little bit of a stronger wind picking up from New Mexico up to eastern Nebraska. And then we talked about tropopause leaves as well, and kind of like, why are these important? Because these, and the breaks in these different leaves, we've got three tropopause leaves. We've got the tropical leaf, the mid-latitude leaf, and the polar leaf. The subtropical jet stream is going to form in the break between the tropical leaf and mid-latitude leaf at about 30 degrees latitude, and then the polar front jet, rather, PFJ, is going to form in the break between the mid-latitude leaf and the polar leaf. All right, I hope you enjoyed the presentation. That's all I got for now. We're watching the tropics carefully. Debby is down in the eastern Gulf of Mexico right now, and Debby is strengthening under very favorable conditions. But we'll continue to watch that here at Spot On Weather. I haven't really made a special video at this point on the tropical outlook for Debby. It's a really tricky forecast with Debby because there's a lot of weak steering winds aloft, specifically off the southeast coast. After it makes landfall into the Big Bend of Florida, it's going to come back over the western Atlantic, and there's just a lot of competing influences going on. The winds are just so light, the steering currents could be very, very big rainfall totals for Georgia and South Carolina specifically. But I've got a lot more training ahead, so I hope you enjoy these presentations. You learn more each and every time you watch this. Thanks for subscribing to the Spot on Weather YouTube channel. Until next time, take care and God bless everyone.